An object moves in a straight line according to the velocity versus time graph shown. Part A. Rank the distance moved by the object in each of the four labeled regions of the graph from greatest to least, and if it moves the same distance in two or more regions to indicate that. So, on a velocity versus time graph, the displacement of the object is given by the area under the graph. This is asking you to rank the distance, which is just the absolute value of the area. We don't care whether it's positive or negative, we just care the area as the distance between the graph and the time axis. So, in region 1, you can see there are a total of 4 squares. In region 2, you can see there are a total of 3 squares. In region 3, we've got these 4 squares. And in region 4, we have these 9 squares. So the number of squares would correspond to the area, which corresponds to the distance. So region 4, with the 9 squares, would be the greatest distance. So we can put that as 4 comes first. That is greater than, and then regions 1 and 3 are tied. So I'm going to put greater than 1, which is equal to region 3. And then region 2, which has the 3 squares, is the least. So that's greater than region 2. And for your justification, you can just mention something about distance being the absolute value of the area, and just talk about the number of squares in each of the 4 regions. Part B. Using just the graph of velocity versus time, is it possible to determine the position of the object at t equals 3 seconds? The answer to this one is no, and the justification for that is that when you're given a velocity versus time graph, unless you know the initial position of the object, there's no way to know what the position is, because the object could have started at 0 meters, in which case it had an initial velocity of 10 meters per second, or it could have started at 40 meters and had an initial velocity of the 10 meters per second. We don't know where it started, so we don't know where it's going to be at 3 seconds. Part C. There are 2 times after t equals 0 when the object passes through its starting point during the 10-second time interval. Is it possible to determine these 2 times? Since we're not looking for an exact position, we're just looking for how far it is from the starting point, which in this case we want it to be 0 meters from the starting point, because we want it to pass through its starting point, we can determine this from the graph. So the way to do this is think of each of these regions in terms of the displacement. Above the axis is positive, below the axis is negative. So in region 1, we have a total of 4 squares. So let's just think of this as an area of, let's just call it 4 for right now, even though we're not actually calculating the area of this rectangle. And then region 2 has an area of negative 3 squares. Region 3 has an area of negative 4 squares. And region 4 has an area of 9 squares. So we want the positive areas to cancel out with the negative areas. That would mean the displacement is equal to 0, and the object's back where it started. So we have the positive 4 squares here. Then we're going to subtract off 3 squares as we go from 2 to 5 seconds. So now we're down to positive 1 square. If we go 1 more second over to 6 seconds, we've just added 2 additional squares on there, which is two additional negative squares, but that's too much. So we just actually want to add on half that amount, because if we go up to 5.5 seconds, that's the equivalent of adding on just 1 more square. It's 1/2 of this square and 1/2 of this square. So at 5.5 seconds, we've had a positive 4 squares and we've had a negative 4 squares. If we kept going, so let me go ahead and write down the 5.5 as one of the answers. So 5.5 seconds. If we kept going on this graph, you can see that we have the positive 4 squares, then we get to the negative 3, and then we get to negative 4. So 4 minus 3 minus 4 gives you a total of negative 3 right now. If at 7 seconds I go 1 more over, that's adding on these 3 squares right here. That's a positive 3 squares, which is exactly what I need to bring it back to 0. So at 8 seconds, we have the same number of squares above the axis that we have below the axis. So the positive and negative displacements cancel out and bring you back to 0. So the second time would be the 8 seconds. Part D. Now assume the object is located at x equals 10 meters when t equals 0. So in other words, they're giving us the initial position. So right here is where the object is starting. So we'll put a starting point on the graph at 10. So that's my initial dot. And we want to draw the rest of the position versus time graph on those axes. So we'll have to know what the exact amount of the displacements are in each of the 4 regions. So instead of just putting things in terms of the total number of squares, now I actually have to calculate the displacement in each region. So region 1, this is a rectangle that is 10 by 2. So a 10 by 2 gives us a total of positive 20. So I'll go ahead and write these on the graph. So this region is positive 20. Next one is a rectangle that is 3 by negative 5. So that'll be negative 15 for region 2. Region 3 will be negative 20. And region 4 would be positive 45. So starting from that initial 10 meters, we're going to first go up by 20 over the first 2 seconds. So that'll go from 10 to 30. So I'll put a dot at 30 at the 2-second mark, and I'll connect those 2 points. That's the first part of the graph. Then it's going to go down by 15 because we have this negative 15 right here. So it goes down by 15 over the course of the next 3 seconds. So if it's at 30 right now, it wants to go down to by 15 to 15 by the 5-second mark. So we're going to put a dot right there. And connect those 2 points. And then in the next part of the graph, it goes down by 20. So if it's at positive 15 right now, to go down by 20, it'll take it down to a negative 5 over the course of the next 2 seconds. So at the 7-second mark, it will be at negative 5. So we're going to put a dot right there. And we'll connect those 2 dots with a straight line. And the final part is it goes up by 45. So starting at negative 5, it's going to go all the way up to 40 over those last 3 seconds. So the final dot is going to be right up there. And we'll try our best to connect those with a straight line. Didn't work too well. Let me try that again. Right there. And that is what the graph should look like. Just one final note on this problem is that you can actually go back and confirm the answer to part C now. In part C, we said the object passed through its initial position at 5.5 seconds and at 8 seconds. And if the initial position is 10, look where the graph next passes through 10 meters. It's right here, which is at 5.5 seconds. And then it's right here, which is at 8 seconds.